In this section, we're going to look at what is it that you have to be a function. Well, let's start out with a basic definition of just a relation. Let's look up here, and we're going to state the domain and range of a relation. Notice a relation happens to be just a set of ordered pairs. Nothing in particular, just a particular set. Now, if we're going to state the domain and range, the domain is just the set of all the x coordinates. The range is a set of all the y coordinates. So we have domain, range. If we want to list them here, the domain is the set of all the first coordinates, x coordinates, or sometimes referred to as the first component. So here we have -3, +3, 0, and finally at the end there, 20. So the domain of this relation is simply -3, 3, 0, and 20. Now let's try to find the range of the same relation. The range, remember, is the second coordinate or the y coordinate or the second component. So let's look at the second components or entries in each of our ordered pairs, and we see that the only two different ones we have -5, 5, -5, and 5. So because we don't have to relist any of our domain, or excuse me, any of our range here, we're going to list our range as simply -5 and +5. So for this relation, here we have the domain, -3, 3, 0, and 20, and the range is the set of -5 and 5. Now that we have a relation, let's see what is the difference between a relation and a function. In our second example here, we're going to determine whether the relation is a function. Well, at first glance, you may not see any difference between this here and what we have up here. You're right, each of these two are relations. But what makes a relation a function? Well, the following rule will do that. A function is a relation where all first components are paired with exactly one second component. Or in other words, every x value is paired with exactly one y value. Let's see if either of these relations qualifies itself to be a function. Let's look at our first relation. We have -5, -6, 9, 30, -3, -3, and 8, 30. Let's check all of our first components or our x values. -5, 9, -3, and 8. Notice they're all different. Because they're all different, every first component is paired with exactly one y component. So since it satisfies the definition of a function, we can say yes, this first relation is indeed a function. Let's look at our second relation. 60, 30, 40, 20, 20, 10, and 60, 120. Do you see something unusual about the first and the fourth ordered pairs? Notice here, the first component is 60, and it's being paired with the second component of 30. Notice down at the end here, I've got that same first component, 60, being paired with but a different second component, 120. So what's happening? I have an x value that is not paired with exactly one y value, or I do not have a first component being matched with exactly one y component. So this here, because I have 60, 30, and 60, 120, that breaks the rule of becoming a function. So this relation is not a function, but simply a relation. So the answer here is no, I do not have a function. So again, what's the difference between these two relations? The first one is that every first component has a different partner. Over here, this first component has the partner of 30, and this one also has 120, so this entry violates the definition of being a function. Now that we've looked at some numbers there, let's look at a graph and see what exactly makes up a function. Let's look at the following. Let's look at graphing the following equation. Y equals x squared minus 2. Now, we're used to graphing linear equations, or we're used to graphing things that turn into lines. Let's see what happens here when we have this x squared term. Well, using all the algebra knowledge we've gained thus far, if you were asked to just go ahead and graph this equation and you weren't sure what it was going to look like, you could at least start by picking a few points that make the equation true. So that's exactly what we're going to do. What we're going to do here is look at our equation and just start choosing values for x and calculating values for y. So here we go. If x is equal to 0, this gives me y equals 0 squared minus 2, or simply y is equal to negative 2. Let's try some more points. Let's let x equal 1. If x is equal to positive 1, this gives me 1 squared, or 1 minus 2, which is negative 1. Continuing along, because we need to have a group of ordered pairs here to see exactly what's going on in our graph. Let's try a negative value. Let's try negative 1. If x is negative 1, notice what happens here is I still get positive 1 because I'm squaring it. So positive 1 minus 2 is still negative 1. Let's continue. Let's try the number 2. If x is equal to 2, I get 2 squared, which is 4. 4 minus 2 is 2. And let's also try negative 2 while we're at it, because we know that if we square negative 2, we'll also get positive 4. Positive 4 minus 2 is still 2. Now, by our definition of a function, do these ordered pairs satisfy the condition? Is each first component being paired with a different second component? Well, look, all of these first components are surely different, aren't they? So none of these are being paired with the same, each of these is being paired with a unique second component. So yes, it does satisfy the condition of a function. Let's go ahead and plot this, and this will give us an idea of what functions look like. So we're going to plot the point 0, negative 2. So we'll start here at 0, go down 2, and put a dot. 1, negative 1 means I go over 1 and down negative 1. Negative 1, negative 1 means I go to the left negative 1 and down negative 1. 2, 2 means I go over 2, up 2. This should be easy for you now. And then finally negative 2, positive 2, and there we have it. So you can see this is forming kind of a U shape. So we're going to go ahead and connect these to the right and to the left. And this is an example of what a function looks like. Now think about it. Remember that every first component has exactly one second component. So in other words, all these x values here, if I had one x value here, I would not have another y value either above it or below it. So what we can do to check really easily to see whether a graph of a function, a graph of a relation is a function, is we use what's called the vertical line test. And that says this: draw as many vertical lines as you need to through the graph that you're examining. If every vertical line crosses your graph in exactly one place, then yes, you have that function, because that tells you that every x component has exactly one y component. If it crosses in more than one place, then it fails the vertical line test and it is not a function. Now that we know that rule, let's take a look at a couple of graphs and determine by using this vertical line test whether or not we have a picture of a function. So let's go ahead and let's draw here quickly some x and y axes. So we have x and y, and x and y. And then what we're going to do on our x and y axis is look at a couple of pictures and determine which one of these satisfies the condition of being a function. Let's go ahead and first of all draw this one here. So we're going to determine whether this relation is a function. Let's draw another one that looks something like this. Let's put a little curve in it there. And then let's look at one here. All right, so we've got three different diagrams. Again, we're going to utilize the vertical line test to determine whether these relations are indeed functions. Let's look at our first one. Remember, the vertical line test says draw as many vertical lines as possible. If it crosses the diagram in only one place, then yes, it's a function. We can see clearly that if we draw a vertical line, we intersect many points at once, so this is no, not a function. This one's not a function. Let's look at our second diagram. Our second diagram has kind of a swirly S-looking thing. Again, is it going to pass our vertical line test? Draw as many vertical lines as you need to through the diagram. As long as you cross in only one place, then yes, you're a function. So this one here is yes. Don't you like the vertical line test? It's pretty easy to visualize, isn't it? Look at the third diagram. Does that pass the vertical line test, yes or no? You're right, the answer is no, because if I draw a vertical line, for instance, here, I cross my graph in 2 points, giving one x coordinate, two y values, so this would be, again, no, not a function. So now that you know a little bit about functions, go ahead, have some fun, and do some calculations on your own.